There is one more aspect that we need to discuss, and that is on multiple outputs. How do we handle multiple outputs? Till now, we have been studying a single output voltage coming out of the DC-DC converter. But in practice, you will see many power supplies, and most power supplies have 5 volts output, 3.3 volts output, 15 volts output, minus 15 volts output, plus minus 12, so on and so forth. So most of the commercial power supplies that you have that are available will definitely have multiple outputs. However, if you look at the DC-DC converter that we have studied, the control input is only the duty cycle to the switches, and there is only one duty cycle available for you to control. In such a case, with one control input, which is the duty cycle, you can control only one output. What to do with the other remaining multiple outputs? How to get regulation out of them? Now that is an issue. So that is the focus of the discussion in this particular video capsule. I will discuss a couple of methods with which you can address this particular issue that I mentioned, and how you can regulate the other outputs of the multi-output converters.
So let us discuss multi-output converters. Multi-output converter. How do they look like? Take for example the flyback converter. Now the flyback converter, let me draw the schematic. It has a primary winding, and I will place a switch like this, ground, and it has a secondary winding. Now this pole is acting like an inductor, and let me put the dot polarities like this. Now recall our earlier discussion on flyback converter. And this is the flyback converter. Now how do we regulate the output V0? We can regulate this output V0 by means of the closed loop control topology that we have just discussed, and is as well applicable to even isolated converters. So what we can do is, let me change the color. We can sense V0, and give it to a controller. Now I'm not going to put the controller in detail. I'm just going to say this is V0 ref, this is V0 feedback. This goes to a controller. It's a PI. Let's put it as PWM, and drive controls the IC. And this is actually the feedback voltage. However, remember that we did go to great lengths to create an isolation between the output side and the control side, and the moment you use a conductor to measure, sense, and then give it back into the control side, the isolation is lost. So therefore, in order to maintain the isolation between this portion of the circuit and all the downstream portion and this portion of the circuit, we would like to have an isolation barrier here even during sensing, and normally this is done with optocouplers. So how this is done is as follows. So let me now erase this portion of the circuit, and at this point introduce an optocoupler. Now what is an optocoupler? You allow some current to flow through the diode like this. Probably I could use a Zener, and I am not going to connect it to this ground. I am going to have a different circuit ground, which is this. So it now appears that there is a current flow from this output. It flows through this diode, Zener, back again. So it keeps circulating in this fashion. So what is the current value? So in order not to short circuit, I will introduce a resistance here, and that is done in this way. Okay. So let me now put a resistance here. So now if you look at the current that flows through I here, it will be equal to V0 minus Vz. You see, this is Vz minus any diode drop, if you want to incorporate the diode drop, minus Vd. We say this is Vd divided by R, and R is the impedance in this series path. Now this is the current that is flowing through this diode. Now suppose this diode was part of an optocoupler, meaning when a current flows through it, there is a light output. Now this light output is connected to a control switch line. Now this control switch, let's say I place it in this fashion. Now see that the control switch is having a ground which is the same as the control portions of the circuit. All these have the same ground. Now the optocoupler's BJT part is having the same ground. So what happens in effect is that as the current flows through this, there is a light output which is actually acting like a base drive for this BJT, and tries to bring it or bias it to its linear region. More the current, more the bias, and lesser the VCA drop across the transistor. Lesser the current, lesser the base bias, more towards the cutoff, and more is the VCA drop across this transistor. So therefore, as the voltage here is changing, which is what we want to sense and feed it back, the current here changes, and the voltage drop across this also accordingly changes. Now use that as a measure. Use the voltage drop across the VCA of this optocoupler output as a measure for change in the output voltage, and use this for feeding back appropriately. Appropriately, you can tap the voltage at the collector point or the emitter point to see that the overall the closed loop is negative feedback. That is important. So therefore now you have a means of sensing the output voltage in an isolated manner. Now this portion will be the optocoupler. I have just indicated to you the optocoupler action, and I have just drawn a line here to this point, but there are other parts, other circuits that will come in here, anti-alias filters and attenuators, or probably even amplifiers that will come into the picture at this point. Anyway, this is how you would feedback with incorporation of an isolation, an opto-isolation in closed looping isolated converters. Now, the next important point that you should see is that with one control topology circuit, you can control one set of switches, either this or in the case of the push-pull, full bridge and half bridge circuits, you can control the other switch too, that is other set of switch, because the duty cycle are coupled in the sense that the same duty cycle can be applied to the other set too. Only thing is that they are mutually exclusive. When one switch is on, the other switch is on, and the other switch is on, the first switch would have been off. So therefore, still control input wise, there is only one control input, which is one single duty cycle control, which can control one output. So one output of the multi-output flyback converter can be taken care of in this control manner. What about the others? So now let us look at that particular problem. So now assume that I have two more windings like this. All wound on the same core. So this will become V01, this will become V02, and let us say, for example, I have one more. And that is V03. And all these are on the same winding, and which means that they are all coupled, and I am indicating the coupled by these lines. Now you can put the dot polarities too. So let us say only one among the two are given back for feedback, and let me indicate the isolation sensing boundary, optocoupler boundary in this fashion. So let us say that you have used optocouplers, sense the output voltage and send it back for control. So V03 is regulated, but V01 and V02 are not regulated. What do we do? So one very popular method which people use is to use linear regulators. So normally the highest power output, the output that is supposed to handle the maximum power, the large power, is given by closed loop. The other low power ones are handled by small 3-terminal regulators called linear regulators. So there are many linear regulators. You may already have heard of the 78XX series, which means 7812 means 12 volt regulator, 7815 is 15 volt regulator, 7808 is 8 volt regulator, so on and so forth. That is one such series, but there are many manufacturers and many 3-terminal regulators. Now you also have lots of low drop regulators. What it basically means is that you now have a load here. This is your R0, and the load is not connected here any longer, and what is the drop across this? So So V drop, I would say V drop. Now V drop is it has to be compensated by this DC-DC converter output, and therefore accordingly the windings of that particular supply should be enhanced to take care of this V drop. So in the low drop regulator, this V drop value is very small. So typically V drop is of the order of 3 volts. In most of the normal regulators, a minimum of 3 volts will drop, has to drop across the regulator, which would basically means if your output spec here is V01 and the spec at the output of the spec at the output of the DC-DC converter here should be V01 plus V drop of the regulator. So if it is 3 volts, it will be V01 plus 3 volts. Not only that, you have to enhance the power spec also, because the windings will have to carry that extra power. So if you have a load current I0 max which is flowing through R0, now I0 into V drop is also the power that this particular winding has to handle. So P01 has to handle I0 R0 plus the extra amount of I0 into it should handle I0 square R0 plus I0 into V drop. Now this is the excess power that the DC-DC converter should be capable of handling to take care of this V drop there. So the current carrying capability and the size of the core may slightly increase because of this. If one uses a low dropout regulator, V drop can be as low as 0.5 volts, and you will have a very less dissipation and dropout there, and you will not lose out much on the size of the transformer core. Likewise, for the other winding also, likewise for this other winding too, you can put a 3-terminal regulator and accordingly adjust the output required or output requirement of the regulator of the DC-DC converter. So with the regulator, what will change is only the V0 requirement and the power requirement, output power requirement for the regulator, and other portions of the design will still remain the same. You can still use the Octave M file, design file, to do the design of multi-output regulators. And in fact I have put up in the last week's this one an example of the flyback with multi-output. You can now study that in this context of what we have just discussed now. So this is one method in which you address the regulation of all the outputs of a multi-output converter. I shall now illustrate another method of tackling this regulation of multi-output converters. So let us say I will take the same example of flyback, but you should understand that you can apply these principles to any of the isolated converters. Not necessary that it should be a flyback, it could be a forward converter, it could be a push-pull converter, it could be a half-bridge converter, or even a full bridge converter. So now let us say that we have these two outputs. I just taken two without loss of generality, and let us say the bottom one I will feed it back through a opto isolation barrier, so we are not disturbing the galvanic isolation that we have achieved by use of transformer. Now with this we can regulate V0 of this, so this is regulated. But how to regulate this voltage? So in the discussion that we just now had, the previous model method, we had used a 3-terminal regulator, a linear regulator. The problem with the linear regulator is that it is dissipative, and therefore the efficiency comes down and the size becomes higher. So therefore the plan now is that we will try to use a non-isolated converter here. So this is an input to the converter. Now let us say you want to have a buck operation. I can use a buck converter like this, and have an inductor, capacitance, and a circuit something like this. Now driving this device is better if you push this device onto the negative rail, that is the return rail, so that you can drive with respect to its base if it is on the return rail. Or if you want to keep it on the upper rail, you can use a PNP transistor or a P device. Now let me just show simple blocks of the circuit so that all would be referred to this particular ground. So now let us say that I replace this BJT with a PNP type. So we could have a BJT something like this, PNP based. So let us say we have a small resistor drive like this, and I bring that out. Now this gate drive can come from a standard modulator. Now standard modulators are available in the market, very inexpensive. For example, TL494 is a typical modulator which is commonly available. It is around 10 to 12 rupees, and this will generate PWM. You have to give it a supply, and it should have a ground. So let us say I choose this as the ground, and you refer it to that ground. So still there is no link to the ground of the other side. Now the output of the regulator itself can be the supply. The output of the DC-DC converter itself can be the supply. Now you may ask a question, the output of the DC-DC converter is not regulated, so then can it act as a supply for TL494 type of devices? Now this is a PWM IC. You can ask in the market for a PWM IC. Most of these type of PWM ICs, you also have another name, I can say SG3524. SG3524. This is also a PWM IC, very inexpensive. They have very large supply voltage range. In fact, TL494 goes from 8 volts to 30 volts, and likewise even the SG3525 to 4. So which means that these PWM ICs can take unregulated voltage for their VCC. So this would give out a PWM which will drive this particular device on and off. And most of the ICs, they have inbuilt internal op amps too, which can act as comparators and difference amplifiers, and also even PI controllers. You can make a PI controller with an op amp using a very simple circuit topology like this. So let's say I have ground. So this is a resistance, and let us say you have a capacitance across the output and the minus supply, and you are having an error coming in through here. Now this is an integrator. So this integrator is like an eye control, and you can also make a PI controller by also including a proportional part of the for this controller. So you have the proportional and the integral controller. So this would be a PI controller. So with one op amp, there are normally 1 to 2 op amps available most of these PWM ICs. So one op amp can be a controller, one op amp can be a difference amplifier, and things like that. So you feed in the voltage to the controller and to the appropriate pins. Make use of the internal op amps to make the difference out of that. The error of that, feed it to the other op amp within to make the PI controller, and that output is fed to an internal PWM. So there is facility for setting the frequency of your switching frequency for this buck portion of the converter with the help of timing resistor and capacitors. So these would be the RT and CT for the local PWM IC. Now this PWM IC is referred, this PWM IC, the ground is referred to this output itself, which is also same as that of the input, and input to this buck regulator, and the output of the PWM is directly controlling the switch, and the output of the PWM is coming out of the controller, which is within this, and you are feeding the sensed output in here. So this portion, this green portion which I am showing here with the mouse, is a full-fledged closed loop buck regulator that we discussed till now and even simulated. Now instead of the linear regulator, this buck regulator can replace that, and then this will definitely have a much better efficiency, because this will not interpose except for the on-state drops and things like that one. The efficiency of this will be much higher than the linear regulator. So one can use one of these types of non-isolated regulators, non-isolated DC-DC converters, to act as regulators in multi-output converters. So that way all the outputs of the multi-output converter will be regulated and give you proper and expected outputs.